G'day everyone, in today's short Chem Help video we're going to look at buffers. What is a buffer and how does a buffer respond to added hydronium or hydroxide ions? So let's just go through some quick definitions. What is a buffer? A buffer is a solution that resists change to its pH when small amounts of acid or base are added. Small amounts, that's the key. You add a bucket load of stuff, it's going to change the pH for sure, but for small amounts. We see buffers a lot in nature. There's one in our blood. That happens when we exercise, we get a buildup of acid, lactic acid and things like that. If there wasn't a buffer, our blood pH would spike and we die quite quickly through acidosis or alkalosis in another system. Seawater, river systems, there's a lot of natural buffers out there. We're going to look at some very simplistic buffer systems, but all buffer systems share these things. They are a mixture of a weak acid and a conjugate base, often in equimolar quantities. That's important, but we'll come back to that later. What they do is they have the capacity to resist changes in hydronium or hydroxide ions that can be added to the system. So what happens? Added hydronium ion from any acid reacts with the conjugate base to form more of the weak acid molecules. Now, weak acid molecules, remember, predominantly exist in the unionized form. So when you add the hydronium, they're sort of sucked up by the conjugate base to reform the unionized acid molecule. So you do make more of those, of course, but because they don't ionize fully, there's little effect on the pH because pH is only due to hydronium ion concentration. So therefore, the acid is neutralized when you add it. Now, what happens when you add a base? Any added hydroxide ions react with the weak acid molecule, forming a salt plus water, so the conjugate base, which itself is weakly basic. Whilst more of the conjugate base is produced, its very weakly basic nature means that the pH is not changed very much and hydroxide ions are neutralized, so they're removed by reaction with that weak acid. So buffer behavior can be viewed from the perspective of shifts in the position of equilibrium, and collision theory can be applied to predict the response of a system. Now remember that in the year 12 course as it stands at the moment, Le Chatelier's principle can only be used to predict. If we want to make an explanation, we need to use collision theory, so remember that. Okay, so let's look at an example. What we've got here is the simple buffer system between ethanoic acid and its ethanoate ion conjugate base. So let's see this one. Okay, so here's our equation. You can see that we've got ethanoate ion, an unionized weak acid molecule on the left with water. Now remember, water is not in the equilibrium expression in the liquid form. On the product side, we've got hydronium ions and we've got ethanoate ions. So what happens when we add acid? When we add acid, the concentration of hydronium ions increase, and thus the number of particles on the product side increases. So the reverse reaction, which has more collisions, will overtake the forward reaction. The hydronium ions are consumed and the equilibrium shifts to the left. Because the hydronium ions that you added are consumed as the forward reaction overtakes the reverse reaction, the pH remains very similar. So the buffer has done its job. What happens when you have a base? So there's our equation again. Added base. The concentration of hydroxide ion increases. Now hydroxide ions, as you can see in the equation, aren't there, but hydronium is. And when you put hydronium and hydroxide together, of course you get water. So adding the hydronium and the hydroxide together, when you add the hydroxide, makes water. Thus, the reverse reaction rate drops because there's less collisions between particles on that side of the equation. The forward reaction, which is unaffected, overtakes the reverse reaction and the equilibrium shifts to the right. The hydroxide ions that you added were neutralized by turning into water with hydronium and the pH remains very similar. So what we've got here is response to hydronium and response to hydroxide. So the extent to which a buffer can resist changes in pH, of course, does depend on the amount and the concentrations of the weak acid and its conjugate base. If the components run out as a result of excessive addition of acid or base, then the buffer no longer works. So that all comes under something called buffer capacity. So it'll stop working once the weak acid or its conjugate base run out. Buffer capacity depends on two factors. One, the relative concentrations of the weak acid and its conjugate base. The most effective buffers have an equal proportion of each. Now that's not normal for a weak acid and its conjugate base. If you think about the equilibrium expressions and the Ka values, Kas are usually very, very, very small. That means the reactants are heavily favoured and there's hardly any products. Well, the buffer system is quite artificial in that way. we've got a lot more of the reactant particles, the conjugate base, than what would normally be in a normal weak acid. So a normal weak acid, just a solution of vinegar, for example, isn't a buffer because it hasn't got enough of the conjugate base there. The actual concentration is also important in terms of buffering capacity. The more you've got, the better it works. That's kind of simple maths there. Anyway, so I hope that's helped you out in understanding buffers, what they are, and how they respond to hydronium or hydroxide ions. So good luck.